Okay, so for one, we're doing a couple initial value problems to just get you started, and I'm going to do just a couple examples to try to help you guys with the work here, and then go over a couple definitions as we go along with these types of questions. So on the first one that we want to find a member of the family of functions. So when they say family of functions, they're talking about, when you solve a differential, here's our differential, and when you solve the differential, you get a couple constants in there. So this is a pretty straightforward problem that we've seen before, but basically what you're doing is you're using the initial values that are given, and you're just trying to find C1 and C2 for a solution here. So the first thing I'm going to use is this first initial condition that I have, and I'm just going to put 0 equals C1 e to the 0 plus C2 e to the negative 0, but that's still 0. So here we get an equation of 0 equals C1 plus C2. Now let's use the second initial condition with our derivative, but we do need our derivative first. So my derivative here is going to be C1 e to the x minus C2 e to the negative x. So just remember, because of that negative there, that should be negative because you're taking the derivative of the exponent. In this one, if we plug in our next initial condition, I'm going to have 1 equals C e to the 0 minus C2 e to the 0, and that gives me another equation of C1 minus C2. So these are two of the equations that we have, and we're going to solve for C1 and C2. So this is just going back to algebra. You could add the two functions together. We'll get 1 equals 2C1. So I know C1 is going to be 1/2, and then if I plug it back in, it doesn't really matter which equation, right? Say we plug it into the first one, you will have 1/2 plus C2, so C2 has to be negative 1/2. And now we get a solution for this as y equals 1/2 e to the x minus 1/2 e to the negative x, and that would be your solution, or a member of the family of solutions, right? So that's the first example that you get here. Okay, the next one is they talk about find the interval centered about a value. So in this case, x equals 0, okay, for which the given initial value problem has a unique solution. So again, talking about a couple things, standard form of any differential that we have, we want to get this to just be 1 times the derivative. So I'm going to divide out that eventually, but it should look like, say you have second order, right? Because that's what we're dealing with. You're going to have y double prime plus some function of x, y prime, plus some function of x, we'll call it q of x, y, and then it equals some function of x, so let's say r of x, right? So that's if it's a second order. If it's third order, it continues, right? Third order, you're just going to have your third derivative plus, and then the same idea, like p of x, q of x, first derivative, plus r of x times the function, and then equal to, let's say, s of x as our last one there, right? So that's my first step. Is anytime you have this notation, we want to get this solved to be in standard form. So this is standard form for our problem would be y double prime plus 3 over x minus 2, y equals x over x minus 2. Then what I always do in these is, what is my domain? Well, my domain is for all x except, right, we don't want it to be 2. But you got to go through what was the initial conditions given. So you could see that they're talking about centered around 0, right? So our initial conditions are in 0. this is centered around 0. So I want to get an interval, right? So if I was doing my domain here, I would have negative infinity to 2 union 2 to infinity. And now, which interval do I pick? Well, where does 0 fall? So since 0 falls in this first interval here, that's the interval that I want to use with it being centered at 0. Okay, so that's talking about the interval centered around, which is going to give us a unique solution. So that's what we're using there. Okay. The next example that I have is going to be determining whether a member of a family of functions can be found that satisfies the boundary conditions. So if you notice, here what we have are some conditions that are given, and we want to see if we do get a solution or not. Okay, so when you're doing the first one, right, we have to do the derivatives here, which is going to be, you know, let's do that first because we need to have our first derivative for all of these. So let's get that out of the way. Now here is where you have your product rule. So it's going to look like this, like C1, and then you're going to have e to the x cosine x. So you have a product rule, minus, because the derivative of cosine is negative, e to the x sine x. And then plus, you do the same thing with the next term. Now notice I just leave the C1 and the C2 because they're constants out, and you have e to the x sine x. This is going to plus e to the x cosine x. Okay, so for our derivative, if we want to clean this up, let's just leave it like that because you could see it's slightly different in the sense of, you know, this e to the x sine x with a negative and C2, but you're still going to have two variables there that are different. So, but we could work with that as we're going along, right? So let's do the first, let's do letter A. Okay, letter A. And I got y of 0 is equal to 1, y prime of pi is equal to 0. So I'm going to have, plugging in there, I'll have 1 equals C1 e to the 0 cosine 0 plus C2 e to the 0 sine 0. Well, sine 0 is 0, cosine 0 is 1, so 1 is going to be equal to C1, right? And now if we use this, the y prime of pi is equal to 0, what will I have there? So now I'm going to plug it into this equation, and I'll have, not b, what am I doing? I'll have 0 equals, now I got C1 e to the pi cosine pi minus e to the pi sine pi, and then plus C2 e to the pi sine pi plus e to the pi cosine pi, just like that. Okay, so what does that equal? So this is 0 is going to equal, well, cosine pi is -1, right? So you have negative C1 e to the pi. Sine pi was 0, right? So that cancels out. And over here we got sine pi is 0, that cancels out. And then you have plus e to the pi, cosine pi is -1, so I'll have minus C2 e to the pi. Okay, well, if you notice, right, we already have that 1 is equal to C1, C sub 1. And if I plug that back in, then I'll get negative, whoa, I'll get 0 equals negative e to the pi minus C2 e to the pi. I could factor out I don't even have to factor out. I could just add e to the pi to both sides. And divide by negative e to the pi. So I get -1 equals that C2. So since I get values here, right, that makes sense. Then for letter A, you do have a solution where you could plug in and you'll get y equals C1 was 1, so it's e to the x cosine x minus e to the x sine x. Do I get this? All right, next one we have is letter B. So I got y of 0 is 1, y prime of pi is -1. Yeah, -1. So B. Y of 0 is 1, and y prime of pi equals -1. All right, so, well, we already did y of 0 equals 1, so we know from the earlier one that C1 is going to be 1. This y prime of pi, we have to plug in because we're going to have -1 equal to, I'm going back, I'm going to use what I had up here, right? You can see what I have up here. So I'm going to have -1 equals C1 e to the pi, whoops, cosine pi minus e to the pi sine pi, and then plus C2 e to the pi sine pi plus e to the pi cosine pi. Okay, and so that's going to wind up giving us what? What do we wind up getting there? We wind up getting -1 equals, oh, okay, so C1 times negative e to the pi. I don't have to write it like that. I could do it like I did before. Negative C1 e to the pi. And then here, you're going to get 0, right? Right, so you have plus C2, that's 0, plus pi. I mean, cosine pi is -1, so you have, again, another negative. Sorry about that, I keep getting these texts. So negative e to the pi like that. All right, so let's see, C1, right, is 1, so I have -1 equals negative e to the pi minus C2 e to the pi. So if we add so we would divide whoa. Okay, that's fine. We would divide both sides by negative e to the pi, so I get e to the negative pi minus 1 equals C2. So this solution is okay. All right, the one thing I didn't do correctly, all right, is I want to change a couple things here. Okay, I want to change this to just the function, And same thing with that one, to just the function. All right. So let's bring these last two down. Okay, and yeah, this last one does have a solution, and you can plug back in your C1 and your C2. But let's go over these two here, where they're just giving us using the function this time. Okay, so a little bit different than with the derivative. This one they're just giving us the function. So here, we're gonna have, with that first one we already know, like since what, like for letter C, you know what I'm gonna do, get rid of that, I'll bring that back. For this one, you know that C1, because we've done this before, is gonna equal 1. And now for C2, right, we could do, or now for this next portion, we could have 1 equals C1 e to the pi over 2 cosine pi over 2 plus C2 e to the pi over 2 sine pi over 2. And cosine pi over 2 is 0, so that's going to give us 1 equals C2 e to the pi over 2, and sine pi over 2 is 1. So we know that C2 is equal to e to the negative pi over 2, and then we do get a solution again. E to the x cosine x plus e to the negative pi over 2 e to the x sine x, and there's a solution for that one. Now this next one, I'm going to change it around because I just want to show you one that does not exist. And if you have y of 0 equals 1 and y of pi equals negative 1, we are going to get still the same thing, C1 equals 1. And now if I plug everything in here, I'm going to get C1 e to the pi cosine pi plus C2 e to the pi sine pi, right? So sine pi is 0, that goes away, so you get negative 1 equals, right, C1 cosine pi is negative, so it's negative e to the pi, like this, right? And now if we know that C1 is 1, we would get something that looks like this. Negative 1 equals negative e to the pi. This is not true. So not possible. So this has the boundary value problem has no solution. All right, so I showed you one of those.